Welcome to our afternoon session. And I'm pleased to introduce our second speaker for today, Professor Stéphane Rubin from INRA, maybe under right, France, and who is going to talk about exact Bayesian change point inference.
Thank you. So, thank you again to the organizer for organizing everything and for inviting me. Again, I'm sorry for having missing the first talk of this week's session dedicated to life sciences. So I'm going to present a series of things, and basically there will be 3 parts in my talk, and each line of the co-authors here correspond to one of the parts. So the first part was something we did with Émilie Lebarbier and Guillaume Brigaille, and then something I'm just doing with Alice Clenen. And if I have time, I'll tend to turn to a last example, which is a work in collaboration with Maud Delattre, Céline Lévy-de-Duc, and Tristan Marie-Huard. So first, I'd like to say a few things about some general change point problem you may face when you deal with genomic data. And then I'll enter into the core of this presentation, which is about the fact that you can do Bayesian inference in an exact manner for change point problem. And you can apply this kind of result to do the comparison of change point location when you have several series. And then if I have time, I'll go to this chromosome-chromosome interaction problem, which is a kind of 2D segmentation problem, but that can be casted in a nice framework as well. So obviously there are many change point problems in genomics for an obvious reason, which is many genomic data are collected along the genome. So if you see the genome line as the timeline, basically you end up with the same problem. From time to time, something occurs along the genome, and you want to see when and where. So the typical situation when you have to deal with this kind of problem is when you look for copy number variation in many diseases such as cancer. If you take the chromosome of a sick cell, the number of copies, which should be 2 everywhere, varies, and at some point, instead of having 2 copies, you have no copy at all, or just 1. Or you may also have a 3, 4, 5, etc. A large number of copies, and this is correlated with the disease. You also have gene detection problem when you want to find which part of the genome are indeed transcribed into gene. And you also have protein DNA interaction. That is when you want to find the place in the genome where some specific protein comes and binds to the genome to do the things it has to do. One thing which is, I think you can keep in mind when you're interested in a change point problem in genomic application, it's now the technology we have, which are called deep sequencing technology, are giving data at the nucleotide level, which is the highest resolution you can imagine for the genome. So in some sense, you know that if you deal with the largest human chromosome, which has 10 to the 8 nucleotide, if you have any method that can deal with such a long process, then you're done, because the largest human chromosome will not increase in time. Okay, we had to run with the technology up to now because at the beginning we had probes, so we had a few tens, few hundred, few thousands of probes, etc. And now we have as many probes as we have nucleotides, so it's huge. It's 10 to the 8, so we have to deal with that. But if you are able to deal with 10 to the 8, then nobody will never come and ask to deal with 10 to the 10, except for some organism. I don't know. The human chromosome, the human genome is not the most complex in the world, but it's one of the most complex, and obviously it's one of the for which we have the most interest for personal reasons. Okay, so I just want to make two typical pictures of the data you have at hand when you deal with this kind of genomic signal. So on the first one, it will be typically the situation with the kind of data you have when you want to do some copy number variation, and if you do one of the technology that is a bit vanishing now, which is called microarrays. So along one chromosome, you had something like few hundred or thousands of points, and now you see that the signal goes along, and it varies along the 2, which should be the number of copies we have at every place. And from time to time, it goes down to 1 or 0, etc. But of course, you have plenty of noise around that, and your job is to find where you have changes and etc. If you go to the so this is for if you do a copy number study, but with this technology you could do as well a gene detection or something like that. You can do different. You can address several biological questions with the same technology. So now if I go to the second example, I change the biological question. I want to find where are the genes, And I also change the technology, and I go to what people call NGS technology, next generation sequencing or deep sequencing. So these data are counts, whereas all the data at the top picture were fluorescent measurements, so they were continuous. These are counts. You have plenty of zeros. You can't really see because you have many, many data. And from time to time, something bumps up. That's a place where you have a gene that is indeed transcribed. So you have many differences between the two. The signal above is continuous. The signal below is a count. And here you have few hundred or few thousand. Here you have something like 10 to the 5, and it can go for the largest human chromosome to 10 to the 8. But the thing which is common is that in both situations we want to do this. That is to find where something changes and where are typically the level, the typical signal distribution within one region. So our job is always the same, find the points at where the distribution of the signal changes. And if I showed you these two slides because I feel that it reminds you that in change point problem inference, you have three problems. First, you have to deal with modeling. You have to think of a proper distribution for the data you have at hand. You also have to ask yourself if the data are independent from each other, from one data point to another. You have a huge algorithmic problem, which is the fact that if you do that in a naive way, there is choose nk way of splitting n data point into k segments, and you will never do that as soon as n is a bit too large. So in a naive way, you can't deal with anything. But there is now a very well established and recognized strategy, which is to use a dynamic programming approach, with which you can solve this problem exactly in quadratic time. And one of the funny things, I'll show that in two slides, is that in genomics, the fact that dynamic programming achieves the optimization is not obvious, and most of the lab I know use heuristics and package and solutions that do not use dynamic programming. So in some sense, they just don't solve the problem, but they were the first to publish the paper in the right journals, and so in some sense, they occupy the field. But what I want to mention is that there is a solution. We know how to solve this problem as long as the loss function is additive along the segment, which has obviously something to do with the fact that you assume that the data are independent, at least from one segment to another. And then we often face another problem, which is a model selection issue, where you have to choose how many breakpoints you have along your signal. And for one thing that also deserves to be mentioned is that the regular model selection criteria such as AIC and BIC are just not valid because they all rely on asymptotic approximation that strongly relies on the fact that the likelihood is continuous. And in change point problem, the likelihood is not only continuous, that would be twice differentiable. In change point problem, the likelihood is not even continuous with respect to the change point. So none of these criteria can apply, and you have to derive a specific BIC criterion, such as the one that has been developed by Nancy Zhang and David Sigmund, to be allowed to apply a kind of BIC-like strategy, but you have to derive it explicitly for change point problem. The regular one, the standard one, does not apply at all. So one of the things that I would like to mention is that obviously you have two scales. In some situation, you want to deal with whole genome data. So you take your whole chromosome, keep in mind 10 to the 8, and you want to do something with that, and maybe you would be limited to do quite simple thing, that is just to find the change point. That is, where are they and how many are they? And to do that, if really your signal is a whole genome, it's 10 to the 8, the quadratic algorithm, you can throw them away because you can't deal with that. It's much too long, so you have to derive specific algorithm, and in the first week of the program, there were two talks, at least that I know, one by Paul Fernhead and one by Guillaume Rigaille, which propose almost linear algorithm. So now with such algorithm, again, this algorithm achieves the optimization problem. So they retrieve the optimal solution, that's crucial, and they're almost linear. So such algorithm can deal with whole genome data, but they won't tell you many things about the uncertainty of the change point location, etc. So it's one first question, which is what is the best segmentation? And then you will also, again, need to choose K, and as I mentioned earlier, there were specific criteria that were developed. One in the talk by David Sigmund 3 weeks ago, and then another one that I mentioned in the bibliography. So now I will focus on the second scale, which is a smaller one. I'm interested in in region of the genome where one gene is located, and I want to ask very precise thing. And I want to know the uncertainty of the location of the change point. How many change points? I could ask this maybe in another way. I want to know if my best segmentation is really best, that for example, the second best or the third best, how much is it the best? To what extent is it really the best? And also I want to be able to compare the change point location when I search several series. So because I go to a lower scale, I can ask myself more precise questions than when I deal with the whole genome data. So the last thing I want to show before to go into the details of the small scale, I want to just stay a bit of time on global scale. So this is in the PhD thesis by Toby Hawking, which was defended last year, so I was there as well. And so this guy and some of his colleagues did a kind of terrible work. They took a series of SNP profiles and they annotated them by hand. So they looked at the profile, so it's something like 10 to the 3 or profile, and then by eye they say, in this region, it's obvious there is no change point. Or in this region, it's obvious there is a change point. Of course, for many regions, they just didn't say nothing because it was not that obvious that something was occurring, but they just by hand said, okay, when you look at the data, it's sure that here nothing happened, and when you look at the data, it's sure that here something happened. So as soon as you have this kind of thing, so it took them, I don't know how many days, but in the end, you have a kind of supervised classification problem, so you can draw ROC curve, comparing false positive, true positive, etc. So this is so all these three plots should be superimposed. They've been separated by kind of technology. Our methodology has been proposed, but they should be all superimposed. And so what is obvious when you look at these three plots is that the two that achieve the best ROC curve as the pink ones, and below the pink curve here, there are only two methods, which are the ones that I first mentioned. The one that proposed by Pelt, which is so corresponding to the talk of Paul Fernandez in the first week, and the other one is CGH-SEG, which is the one I was mentioning also by Guillaume Rigaille. So what the first thing that this plot says is that you have to use an exact method if you know how to solve the problem exactly. It seems too stupid to be said, but I do think it has to be said. So you have to you have to use the optimal solution. That's it. And the optimal solution in terms of segmentation achieves the best ROC curve. So this is a good point. And the bad point is that with these two methods, you have a model selection problem. So you have a model selection criterion, which provides you the number of segments that are supposed to be there. And you have these two black dots here and one over there. So here is the black dot provided by the model selection, which is embedded in Pelt. And over there is a model selection, which is embedded with a criterion with another package, but based on the exact solution. And what you see is that although the optimal path is completely well retrieved by both methods, in terms of model selection, they both fail in a completely different way. So much too few or much too... so here you have much too many segments, and you have many false negative, actually, false positive, and here it's exactly the opposite, but in some sense, both fail. I mean, it means that you can't trust them as for K. So it means that the algorithmic problem is solved, okay, and the model selection is not really solved. To my experience, it's still probably the most difficult problem. So now I'll turn to the local question, and I enter to this Bayesian inference and the fact that you can do exact calculation within a Bayesian framework for these change point problems. So just to state the problem, the model I have in mind is the following. It's a purely hierarchical Bayesian model. You first draw the number, so you have one signal. You first draw the number of segments you have in your signal. Then you draw the segmentation. So when you say segmentation, you mean plenty of things. So I will denote it with M, the segmentation, but M is the set of the location of the change point, or the series of segments it defines, or the length of the segment, or everything. M is all this, and then you have to draw your parameters conditionally on the. So you draw the segmentation conditionally on the number of change points. Then you draw the parameters conditionally on the segmentation, and then you draw the data conditionally on all that. So I have a little drawing to be sure that we all agree with that. So you start with you just draw K, number of segments, then you draw the segmentation, you draw the parameters, you draw the data, okay. And our job is, now we're left with that, of course, because we don't know the truth, and we'd like to be able to say something about the conditional distribution of the number of change points, the segmentation itself, the parameters, etc. So actually, maybe this is too ambitious. Maybe I don't want exactly this full, complete join posterior, but there is a series of questions that I would like to be able to answer. Typically, I would like to say something about the number of change points, but I would like also to say something about the fact that it is likely or not that, for example, the case change point occurs at position t, conditionally on k or not. I may want to make this kind of inference with a given number of segments, and I will show you an example where, in some sense, you know the number of segments in advance, but of course there are situations where you don't. You may also ask yourself if there is a change point at a given location, and then also you can want to say things about the reliability of the best segmentation. Is it really best than all the rest? And for example, you can evaluate this kind of thing with the calculation of an entropy term. If the entropy is very, very small, if the posterior entropy of this posterior distribution, the P of m given k, it means that the posterior distribution concentrates really around one segmentation and is very not spread out. So it means that really the best is really the best. And we will see that in terms of model selection, this criterion is really pretty efficient. And then another one, which is, for example, the conditional mean of your signal. If you do copy number variation, at some point, the geneticist only wants to know if in this loci, in this locus of the genome, there is indeed two copies or not. And he may not be interested in the fact that there is a change point on the left or a change point on the right. He only wants to know if this gene has been lost or not. Or if you have 3 copies of these genes, rather than 2, which may be bad depending on the function of the gene. Okay, so if you do the following assumption, what I would like to present you is that if you do the following assumption, then you can compute all the quantity I mentioned above in an exact way, in a quadratic time. So the assumption that I do is the following. The first is that the distribution of the segmentation can be factorized along the segment. So the first obvious prior distribution that you may imagine is a uniform distribution that fits in this assumption, but you can also imagine a prior distribution which favorizes equally spaced segments, if you think that that's how life goes on, which is probably not true for genomic data, but I don't know. So if you just proportional to the product of the length of the segment, it fits as well. Now, if you assume that the conditional distribution of the parameters given the segmentation is also completely factorized, and this is a strong assumption because it forbids homoscedastic model. They're not allowed to share the variance, for example. If you have a Gaussian model, this assumption means that from one segment to another, you can't oblige the segment to share the same variance, okay? Because it would be a parameter that would be shared across the segments. And then if you assume that the data are also, the conditional distribution of the data given the parameters can be factorized along the segment, you just assume that the data are independent from one segment to another. So you may have within segment dependency, but not between segment dependency. So if you have a local AR1, for example, it's okay, but if you have an AR1 that goes along, it's not okay. Okay, so now if you want to, in this framework, I'm going back to 2 questions I asked 2 slides ago. If you want, for example, to do model selection, you want the conditional distribution of k given the data. So basically, this is proportional to the distribution of y given the data given k. And you write down your formula. So it's the sum of all possible segmentation, this mk over there. Maybe I should use this because I'm not that tall. But the thing is that usually I don't know how to use this kind of thing. So, okay, no, I'm going to use my hands better. So you have to sum mk is the set of all possible segmentation of n data into k segments. So you have to sum over this, then to make a product of all the segments thanks to the factorability assumption I made before, and then you have to integrate out with respect to the parameter within each segment. So if you're in the exponential family and if you use conjugate prior, actually the last integral is not a problem. It's explicit, so you can compute this every time. So you're left with a sum of all possible segmentation and a product there. Now, if you want if you care about the fact that there is a change point, the case change point at location t, it ends up with the same thing. Here you have to consider all the possible segmentation of the data from 1 to t into small k segment, and then the rest has to be segmented into capital K minus k segments. So you have the product of 2 terms, but these 2 terms have the same shape as you have below that. And the thing that it's fairly obvious, but computing this kind of sum product is something that we know how to do. It's something you know every day. If you want to compute this, you just build a matrix, an upper triangular matrix, and in each term of the matrix, you put exactly the formula f of r, which is relevant for the quantity you want to compute. And you just take your matrix and you compute its case power. Okay, so you put a matrix which is n by n plus 1 times n plus 1, and each cell of this matrix is just the function that is relevant for the considered segment. And then that's what we do when you do a product of matrix. You do the sum of all possible terms of the product of the term. And then when you iterate, you do this for products of 3 terms and 4 terms, etc. So in the end, you have considered all product of k terms of all possible summation. Because the matrix is upper triangular, you force it to go along the process from 1 to n. Okay, so if you compute that, within each cell of your matrix, you have all the quantity you need for all the calculation that I mentioned before. So the thing is that, it's fairly obvious in a certain community, and especially in maybe it's obvious for most of you. It was not for us before. It's very well known in the computer science, and they call it the sum product algebra. And the thing is that if you use dynamic programming and use this formula and you replace sum with max and the product with sum, you end up with a dynamic programming which provides you the optimal segmentation. So actually, when you do dynamic programming, you do this, but with another algebra. So with this kind of quadratic thing, now you can go and compute the thing you want to compute. So this is a series of examples. So this is the same CGH. So CGH means comparative genomic hybridization. So it's microarray data, not too many points, something like 100. So this is the same data set, and here you have the results when you assume that you have k points, k segments, or 3 segments, or 4 segments. So I don't know if you really see the posterior distribution, but here you have the posterior distribution of the first change point and the second change point, and here you have 3, but there is a green one which is very peaked here and that you can't see. So the important thing is that the 3 distributions here are very peaked, much more than this one, which tend to say that the best segmentation into k segment is much better than the other segmentation with k segment, with respect to the best segmentation with 3 segments, with respect to the other segmentation with 3 segments. This one really much more outperforms its competitors than this one. And if you want to plot one last thing, which is the probability that this segment, I mean, the fact that you have a change point there and then a change point there, the probability that this occurs truly given the data. So you end up with a 2D plot because you have the starting point of the segment and the end point of the segment. And you have these peaks, which tells you how you believe that this segment, with whatever happens before and after, but just this segment occurs. And again, you see that here you have much more peaked distribution than there. So this may be of interest because in cancer, for example, the question is there an alteration between there and there? I don't care of what happened before. I don't care of what happened after. The thing to me is, did I lose a gene or not? Okay, so this is again, you see that here you have more peaked distribution, meaning that this best segmentation is really better than the other. And when you use this kind of principle to do model selection, you can use, so BIC is fairly well known, and basically BIC is just a log probability of the number of segments given the data. So often you take a uniform prior on k, so you end up with computing just that, and the conditioning on y is useless because it's a constant, so this is a typical quantity. But in the mixture model context, people propose this criterion, which is ICL, where you add one more penalty in BIC, which is the entropy of the conditional distribution. And again, this is the thing where you put a strong penalization whenever the best segmentation is not that best. Okay, and this penalty term goes to 0 whenever the posterior distribution is a Dirac mass on one segmentation. And what we observe is that in terms of model selection, this criterion here, where you account for this posterior entropy, achieve much more. Is much more efficient to find the true number of change points. Okay, so you may also notice that you can define BIC in 2 ways. You can define the BIC depending on whether you consider that the model is the number of change points or the segmentation itself. Then you do not compute the same posterior quantity here. So you do not end up with the same criterion. And for example, trying to choose the number of segments, so this is a green curve here, does not work at all. It's better to choose the best segmentation and then to count how many change points you have in this segmentation. So this was actually an old work, and we did that 2 or 3 years ago. And the thing I would like to get into now is an application of this kind of technique to another question, which is the comparison of change point. And this is joint work with Alice Clenen. And the question we have at hand is the following. So I don't know how much you know about biology, so I decided to explain things. So maybe I'm saying things you obviously all know. So the thing is that in eukaryotes, the genes are a portion of the genome that are expressed, but they are not continuous. Then they are separated into several regions called exons. Exons means that they will go out of the nucleus, whereas the region within this portion here are called introns. They will stay within the nucleus and be degraded, and they have no known function. Of course, they have one function. They have to be. And this is a kind of idealistic representation of the NGS technology I was mentioning. If ever you do, you take only the transcripts that are in your cell, you take your reads, you map them onto the genome, and then you have a count. There is saying that I have a small sequence that starts at position T plus 1, etc. I count them, so I have this histogram there. And in an ideal world, I have only a non-zero count in front of the exons, and I have 0 all around. And then I have a pure change point problem, as usual. I want to find the location where the transcription starts and where it ends, and where are the boundaries between the exon and the introns. Okay, so this is the kind of plot you have when you go to this kind of site, or even they're even nicer if you go on the website of the company which sells machine to do NGS, of course. You always have an ideal plot. The real data are more like that. So these are NGS data. It's one gene, it's in yeast. So for these genes, we know there are few genes with multiple exons in yeast. Most of them have just one exon, so it's not fun. You have just one start and one stop. But in yeast, you have some for which you have 2 exons. So this is one example. And so that's why I was mentioning that in some situation, you know the number of segments. Here you have 2 exons, so you need to have 5 segments. One before, then first exon, one in between, second exon, and then one after. Okay. The thing is that these 3 data sets here are the same gene in yeast, but grown under different conditions. And the question, so the blue lines that you have here are the posterior distribution of the change point. So you see that's quite picky. We're quite confident for each of these data sets about the location of the change point. And the question that is asked, and it was really asked for yeast, whereas it's well known, for example, in the human, is are the boundaries the same? Because many organisms play around with this kind of with design, and something you can do is, for example, if you do this, you end up with this light blue line. So you merge all the portion, you have this light blue line, and from that you do a protein, and the protein does something. But you can play a game which is to say, okay, if I remove this, what happens? It's exactly if you have a recipe, you remove one sentence from your recipe, and instead of having pancakes, you end up with, I don't know, fried eggs or something like that. Okay, it means that with the same region of the genome transcribed in different way, you end up with very, very different protein, and it's very well known that organisms do that. There is an example in fly where there is 10 exons, so something like 10 to the 2 to the 10 possibilities, and 800 have been observed, meaning that the fly truly uses a lot. But you can do that, you can remove one exon completely, or you can just read it a bit more or a bit less, and then you don't have the same text, you have one word more, one word more less, and so you end up with something different. So it's known that some organisms do that. The question was, does it exist in yeast? So that's the question. So now the question now is this change point located in the same place across these 3 conditions? Okay? So there is one question which is obvious. Here I have 3 conditions. So the first obviously easy case is when I have 2 conditions. Because if I have 2 conditions, because I know how to compute the posterior distribution of one change point, I have 2 independent series. I just make the convolution of the distribution of the first change point in the first series and the second series. I get the posterior distribution of the shift between the two change points. And from this, I get a posterior distribution, and then for the shift. And then the question is only where does 0 lie with respect to this posterior distribution. Okay, so I have two series. I define delta as a shift between the two first change points. For example, do the transcription start at the same location under the two conditions? Okay, I can compute the posterior distribution, and then I do my calculation, and I'm glad. So I'm almost glad, and this is one limitation. As I was mentioning before, everything goes well if you can compute this integral, meaning that you're in the exponential family with conjugate prior, and if you have no parameters that is shared from one segment to another. Unfortunately, the consensus distribution for NGS data is now the negative binomial. Everybody does that, and it fits the data reasonably well. The bad thing is that the negative binomial is not within the exponential family, as long as you don't know the overdispersion parameter. So it is if you know phi, it is not if you do not know phi. So what we do is that we use a robust estimate of phi that you estimate in advance, and then you do as if you were knowing phi, which is obviously not true. Okay, so if you allow me to use this phi that I compute in some way, then I end up with this posterior distribution, and now I can go back to my favorite gene and see what happens. So these are the posterior distribution, and the pink region are the 95% credibility interval for the location of the change point. And now the game is 0 in this credibility interval or not. For example, here, when you compare condition B and C for the rightmost endpoint of the gene, you feel that there is no significant change between these two conditions, whereas you would probably say that something happened here between condition A and B and A and C for the rightmost endpoint, etc. So you have a first way to make the comparison and to decide if between two conditions there is a change or not. Okay, and one thing which is interesting is that this posterior distribution is often multimodal. And this is typically that you may have observed when you do segmentation. When you have one good solution, the second best solution is often not one data point away, but it could be much further away because it's really a problem of discrete optimization. So there is no reason that two optimal solutions have to be close in space in some way. So the best is there, and the second is there, and the third best will be there. And so you very often have this multimodal posterior distribution. Actually, there are many ways to define this, the 95 credibility interval. We choose one way, and we could probably discuss if there would be another way to do it. So now if I have three conditions, I can do my shift because I have more than two different to do. So you can write a kind of graphical model saying the same hierarchical model, except that once you've chosen K, you draw a random variable which tells you, which, for example, the first change point in all the conditions are the same or not. And based on that, again, you choose your segmentation, you choose your parameter, you draw your data, etc. So the only thing that I did is that I introduced this random variable, which tells me if, for example, the first change point in all my series are the same or not. So it means that the transcription starts at the same location for my gene in all the conditions. So the thing is that doing that, of course, I introduce some dependency between the possible segmentations. They are not independent anymore from one segment to another. All those data would be independent. Here, with this modeling, the segmentation are not independent anymore. And the calculation I presented you before are only doable if the series are completely independent. So there is one way to say, okay, I'm going to draw the probability of my event with a prior probability that will be given by independent series. But if I do that, it's very, very unlikely that the change point will occur at the same time. So in terms of Bayesian inference, I would put a very, very strong prior against the fact that the locations are the same. So I don't want to do that. Otherwise, I will always reject in some sense. So I don't want to do that. But what I could do is say, okay, so let's take the model where they are completely independent. For these guys, I'm able to compute everything, and here again, I'm telling you the same formula for the third time, I would say. Okay, so I know how to compute that, and now I just have to make a change of measure to bring it back to my model, where I just want to say that the prior probability for this event to occur is something that I will tune myself, say 1/2, if I know ID or something like that. Okay, so again, you can compute this posterior distribution probability exactly in a quadratic time, which is nice. So so typically, if I go back to my favorite gene, so here are I can compare the condition 2 by 2, but the most interested line is the last one, where if you compare the three conditions all together, what you see is that basically you think that the internal boundaries are kept. The posterior probability for the internal boundaries to be the same all across all segments, all conditions are the same, but at the external boundary you have changes. And when you go and have a look at all the genes that have two exons in the yeast, and for which both exons were expressed, you end up with the same thing. So here we just played around with this prior probability. Here this is what we did spontaneously because we have no ID, so we put 1/2. And then we go to Sherlock's lab in Berkeley, and their opinion was that you expect that the boundary should be the same almost everywhere, but you most expect that the internal boundaries are preserved and not the external boundaries. And in some sense, so of course it changes when you change the priors. Posterior depend on the prior. You can do nothing against that, but the conclusion is about the same. Internal boundaries are preserved and external boundary may change. The thing is that from biological point of view, people were interested in that because external boundaries are not exactly the same nature that internal boundaries. Internal boundaries are really things that are, when you merge them, everything here has to be transcribed into a protein. But at the extremities, left-hand extremity and right-hand extremity, you have this UTR, untranslated region, which are things which do not go into proteins, but that are used to, in some sense, take the RNA at some place in the cell to be translated into a protein. So it's rather a matter of changing the address of the protein within the cell than changing the protein. It would be the same protein. It's likely that you will have the same protein in the end, but not in the same place. So it's slightly different. Okay, so this was, so hopefully I will maybe have time to introduce you with this last problem. So I put brackets around Bayesian in my title yesterday because this part will not be Bayesian. I don't know how to do that in an exact Bayesian manner at this time, maybe one day. So this is really, really preliminary work, but I thought it was interesting to speak of it here because at first glance, it's a 2D segmentation problem, and I think that we all know that 1D segmentation problem are fairly much easier than 2D segmentation problem, just because you lose the ordering when you go into 2D. So this problem is, at first glance, 2D, but if you cheat a bit, you make it a 1D problem, and so you know how to do it. So that's the summary of the last part. So the problem at hand is the following. Biologists are more and more interested into the conformation of the chromosome within the cell. So a chromosome is long, very long. You have several meters of chromosome within each of your cells. So it's several meters per cell. So it's very, very, very packed, very, very dense. It's really completely messy. And the way it is folded within the nucleus of the cell, of course, has many consequences on many things, including gene expression. And for example, which is something which is very obvious, if the sequence of your favorite gene is completely at the heart of the pack, you have no chance that the transcriptional machinery can access it to make protein from that. So at least the gene has to be, the chromosome has to fold and unfold, and they do this all day long, all second long. Setting one gene at the exterior and then taking it at the interior, etc., so that it's available for the transcriptional machinery. And also, something which is pretty well known now is that you may have one gene there and one gene there, but the chromosome folded so that they go close to space, and so that the transcriptional machinery has less work to do. Once you're there, okay, I deal with this guy and I deal with this guy because they've been brought together. So they're likely to be co-expressed, okay, because they are in the same location in the nucleus at the same time. So there is a series of techniques. So this stuff, the series of techniques to deal with it, to try to access with information, were called chromosome conformation capture, 3C. And then people went to 4C, and then 5C, and then the last name is high C, and have no idea of the next name, which would be I don't know what. The thing is that you end up with a matrix, and the matrix has as many rows as you have loci along your genome, and as many columns as you have loci as you know, because it's pure interaction matrix, n by n. Okay, and here you have interaction. So I was telling you, I have one gene here and one gene there. They seem to be far away, but actually they're close in the nuclear cell. Here, the people we work with are interested with the situation where the genes are not that far along the genome, but you have a block which is very folded, and all these guys are expressed all together because they're close. So they're already close along the genome, but they're even more close in the 3D structure. So the kind of data you end up with is this one. So the first thing you may notice is that it's a human chromosome, so the length is something like 10 to the 7 because it's one of the shortest one. But people compress the data very, very, very much into windows of width, something like 10 to the 5. So I was telling you that the resolution is wonderful. It's a 1 nucleotide, and the first thing you do is, okay, 10 to the 5 nucleotide, and then you end up with a matrix with something like 100 by 100 or 200, few hundreds times few hundred, but something that is manageable, and I can tell you in advance, manageable with a quadratic time algorithm. Okay. If ever we're able to fit that into a linear time algorithm, then we did something because you don't need to do this compression, which is okay. It seems that at this point they still find things that they didn't know in advance, so that's nice. But obviously we'll have to do better than that. So this is the one first paper about this kind of use of this technique was in Nature, and this is a result that is provided, and people use a kind of HMM. So already what they do is that they say, okay, the timeline is a diagonal of this matrix, and I'm going to write an HMM along that and do something and find groups, etc. And in some sense, we do the same, except that we use a change point problem rather than an HMM. So if you see that, these blocks here are blocks of genes that are not very far away along region of the genome, so they're not that far away, but they're more compact than other, because here you have compact here, etc. And you are quite far away for the rest. So when you see this data and when you see this plot, well, you imagine a model like that. So remind that the data are symmetric, so you just have to care about the lower triangular part of the matrix. And you say, okay, I have change points, so these are the limits of my blocks. Along my diagonal, I have square blocks. Actually, not square, it's half square because you just have half of the matrix. And below that, you have noise. Okay, or part of that, you have noise. So the question is, are we able, as usual, to find the location of the change point? So if you write the following model saying that when you're in one diagonal block, you have a certain distribution, depending on the block in which you are, and when you are outside, you have another distribution, a kind of noise distribution, then you can write your likelihood, and your likelihood splits into two terms, one term which is the sum of all diagonal block, and one term which is the sum of the rest of the world, outside of the block. The thing is that if I go back to this plot here, I can split this gray region into rectangle that I can merge with the corresponding diagonal block. The thing is that all these rectangles have to live with the same parameter. So again, it's a problem when you do dynamic programming because you don't want parameter to be shared from one segment to another. So if I rewrite my likelihood like that, I have a sum, and this is an additive loss function provided I know this guy. Okay, but as soon as I know this guy, I take the corresponding loss function and I can apply my dynamic programming favorite dynamic algorithm, and that's done. Okay. The thing is that it's not that difficult to estimate this mu naught, because if you go back to the original data, mu naught corresponds to the parameter which deals with this noisy region, which is actually 4/3 of the data, even much more than that. So what we do at this point is that we cut somewhere here, and we have something like 10 to the 5 data to estimate a mean or something like that, and then we're glad with that. So of course, we didn't get into the statistical properties of this procedure, but that we do. We compute a prior estimate of this mu naught, and then you have a regular change point problem. And so, as usual, we have a second problem, which is to choose how many change points we'd like to put. So we have no criteria. The funny thing is that if you think a bit about this model, you see that whenever you increase the number of change points, you're not making a thinner decomposition of your signal. You're changing the shape of the block. So a decomposition, a segmentation model with 12 blocks is not nested within a segmentation within 11 blocks. So you have no nesting of the model when k increases, which makes that the likelihood does not increase systematically with k. And so what we just observed very empirically is that it started to increase and then it decreases. So now we know the most stupid thing you can imagine. Okay, if there is a maximum somewhere, let's take it. So what empirically the feeling we have is that everybody can have is that we over-segment probably with that. It's not too bad. It's bad, but not too bad. So we didn't do the job. We can reapply the regular criterion because the number of data within each segment, well, we have to accommodate for the number of data within each segment, which is not the same as usual. Probably it's doable. I mean, we're working on that. So the kind of result we get is this. And if you compare with the prior result, which were obtained with HMM and also validated with external data, the correlation is not too bad. We not always over-segment, by the way. At some point, we have a larger segment than the one they have. But of course, there are many things left to do for this problem, which is, as I feel it's a funny problem, I just wanted to share my joy with you. So I will end up there. I have just a bit of advertisement for several packages we've developed. So the first one, which was dedicated for so let's say for microarray data, but basically it means for Gaussian signal. It's fairly complete. I mean, it's segmentation, fast segmentation, but you can use covariates, can do calling, you can do a bunch of things. It's probably the most complete package we have at this time. And people start to use it for other purposes, like environmental data. We had discussion last week about that. So this one, and I want to claim that I'm not responsible at all for the name of the second package. I was not there the day they chose it. But it's the one that does the very efficient segmentation that Guillaume Rigail presented two weeks ago. And the last one is about the exact calculation for the Bayesian inference, change point location, etc. And that's okay.
What was the model that you used for this last discussion, the diagonal?
For this one?
Yeah, what is P of Y given everything else?
For this, we've considered, here the result here are with negative binomial, but you can, we also thought about Gaussian because you make a sum of so many data that the Gaussian is not that bad, by the way. But we use negative binomial because it's NGS. But.
So in this block A figure, you're assuming that the neighboring nucleotides are correlated, but if they're far away, then they don't share any.
Yes, correlated there. Yes, I don't know what exactly you mean by not statistic.
There's
there are in physical interactions in the space. That's what you measure.
I see.
So I didn't get much into this. They actually bind physically.
I see.
And the thing that you do after that is that you do microwave, so you break down the chromosome into small pieces, and then you get these small pieces, you sequence them, and you get your data like that. But you get them by pair. That's the most important thing. You get pairs of sequences that are not neighbor, and then you sequence them knowing they're together, and this is how you get your counts.
So it's discrete data.
Yes, at the origin it's discrete. It's along the chromosome, one per nucleotide. It's discrete. Actually, it's always discrete a long time. You have 10 to the 8 data point, and then it's count. That's why we use negative binomial. But as I was saying, when you make a sum of a 10 to the 5 negative binomial, I would use the Gaussian without.
And so, I mean, when you're talking about all this estimation, you've got all these assumptions to allow your summability.
Yes.
You know, so not borrowing strength. Would it be possible to do like a kind of Markov assumption to, you know, neighboring blocks, for example, to try and allow? Does that?
I fear that this assumption are fairly not this one unnegotiable.
Yeah.
No, because it's really when you do really think of a matrix product.
Yeah.
You took two elements. You're not allowed to have one third term which tell, oh, okay, this guy and this guy also have something more to say. No,
Yeah. So
you can do that. So it's really an algebraic property, at the core of that, and the algebraic property does not. I mean, you know that pretty well. And I don't know what you're feeling in, but my question.
To relax something is the answer. So what we did was
So-
relax the parameters and allow them to be more general, but then we
No.
have to approximate.
Yes.
But we can still use the same product.
At this point, what we do for when we deal with signals that are exactly of what you like what you say is we try to estimate the dependency in a robust way. The thing is that you have to estimate this dependency before to do the segmentation, because you want to do segmentation accounting for the dependency. And once you do that, you whiten your signal, and you can do that actually. We're working on that. You can do that in a consistent way, etc. But in some sense, it's the same as for the phi here. It's a kind of nuisance parameter. If you estimate this guy, and I think the autocorrelation parameter in AR1 could be seen in the same way. If you're able to estimate this guy, in some sense you can remove its nuisance. It's really said with the hands, but but as for the algebraic trick, it's no, you can't.
One question. So earlier you had this picture of one yeast from one gene from a yeast, which are like the three conditions.
Yeah, this one.
This, can you actually do the application to condition A repeatedly, and then see whether there's a variation in the?
Oh, of course. It's here the growth condition were different medium for the growth of the yeast. But I mean, you can do the same a long time. And if your question is, would I be able to test a specific contrast a long time? I would not say so.
Are the change points actually consistent, identical, or there's a little bit
Yes,
of variation?
you can test that. If it's only like comparing several conditions, 10, I can do that. If your question is does the change point move linearly a long time, etc., I don't know how to do that, because this is really purely, again, combinatorial. So we explore the complete space. So no, it's not for a very precise contrast. No, it's just, is it the same or not?
Do you know how robust your procedures are with respect to variation in the priors? Because you're choosing.
It is.
Priors could be very high dimensional.
As for the prior.
I mean, what if you had 100 exons?
So luckily this does not happen, but you may have 10. But which prior specifically?
Well, you went to some length to tell us that the second prior was probably better than the first prior.
Yes.
But to what extent have you experimented with the priors?
Okay. So here, if you notice well, actually, we have only two priors, one for the internal points and one for the external points. So, and we just experiment. So the answer is it robust? The answer is no. When you change the prior, it changes the result. Indeed. Here we are lucky enough to have our favorite biologists were able to say, okay, this is what we expect. So, and it makes a change, of course. But it's always the same when you do Bayesian inference. I never know if it's a good point to be sensitive to the prior or not. In some sense, you want to be, or you don't. Depending on the people, the answer is not the same. So I have no answer to this question.
The point I would make is that it's harder to know what the prior is doing if there are many parameters associated.
So
in effect,
one of the drawbacks of this kind of techniques is that at some point you completely lose the function of your parameter in the calculation, because they are so intricate into elements that are integrals within a matrix that at some point it's making an analysis, for example, of the final result. Well, for this one, I think that P naught is the good guy because the formula is there. So this formula is nice. But any other priors that may affect the prior distribution of the segmentation or something like that, you lose it. It's very, very difficult to have any analytical view of the influence of the prior at this point.
All right, any further questions? Well, if not, let's thank Stephen again.
Thank you.